Hello, everyone. I just want to thank you for all joining us. We'll get started in just a few moments. Hello, and welcome to today's American Nuclear Society events, Robotics and Remote Systems Update from Industrial Partners. I am Adam Carroll, the chair of the ANS Robotics and Remote Systems Division and a senior engineer at Oak Ridge National Laboratory in the Remote Systems Group. I'm excited to serve as the moderator for today's discussion. Before we get started, I'd like to cover a few quick notes regarding today's events. If you have any questions, please type them into the Q&A function. I will attempt to address as many questions as possible. The event will also be recorded, and a link to the recording will be emailed to the event registrants by tomorrow. Additionally, certificates for attendance for the event are available for ANS members by request. Please see the chat to contact information. And finally, we ask that all participants adhere to ANS Code of Ethics and Respectful Behavior Policy, which can be found at ans.org. With those notes out of the way, I would like to introduce you to today's speakers. Judd Lapp is the Nuclear Technology Business Development Manager for PAR Systems, Critical Handling Solutions Division in Shoreview, Minnesota. He has more than 25 years of nuclear power operations, maintenance, training, and program management experience across commercial, governmental, naval, and aerospace fields. Christian Pallone leads the robotics and automation program for the nuclear sector at AtkinsRéalis, assisting clients in developing robotic solutions across nuclear sites in the UK, US, and Canada. He has more than a decade of experience in robotics and automation within the aerospace and packaging industries. And last but not least, Scott Martin is the Managing Director of Veolia Nuclear Solutions, North America. With over a decade of experience, he is a leader in complex mechanical systems, remote handling technologies, and nuclear decommissioning projects. He has spearheaded equipment delivery projects across the US, UK, France, and Japan. Now I will turn it over to Judd for his presentation.
Okay. Thank you, Adam. You should be able to see my screen. Good morning or good afternoon as appropriate. As mentioned, I'm Judd Lapp from PAR Systems, and we'll be covering some of our nuclear robotics. That being said, just a brief background on PAR Systems. Inside of PAR, we have PAR Systems, which is automation solutions. So this is motion control in highly regulated critical industries. We've automated assembly, which is medical device, advanced manufacturing, which is aerospace, and then we'll also talk about Jared with a little bit, which is our mostly mission critical systems for the Navy. And then finally, we'll delve into critical handling solutions, or our nuclear business unit. So we're a privately owned business. same family that owns us also owns the Minneapolis Twins. We are Minneapolis-based, Shoreview, just outside of Minneapolis. And these are some of the highly regulated industries that we serve. In aerospace, NASA Artemis, we do quite a bit of work with them. The orange hue on the cryogenic tanks there in front of you is from our spray foam insulation onto those cryogenic tanks. We also supply the lifting and handling cranes for maneuvering those components during manufacture. And then also our friction stir welding system helps put those together through a pretty interesting and complicated process that we do quite a bit of R&D on. Our adaptive manufacturing is very high precision and control for aerospace and for manufacturing and medical device. So we don't actually manufacture medical devices, but we build the equipment that manufactures those for our partners. Marine and shipboard, this is our Jared division. So elevators for weapons, cargo, and personnel, anchor systems, and fireproof doors, as well as steering gear. So quite a bit of military hardware there. And then we'll focus on our critical handling solutions, a couple project highlights today that kind of get into what PAR is doing on robotics side of things. So this is our nuclear group where I have the pleasure of working. Focuses on cranes and environmental manipulators like hot cells, laboratory work. Those are the kind of things that critical handling solutions is working in. So our remote handling solutions are since 1961, when PAR was spun off. We've developed remote handling systems for some of the most difficult deployment in the world. Capability and quality is demonstrated through longevity. We have a system out at NASA at their Get Flight Center that's been in operation since 1963. And one of our systems at Argonne National Laboratory was out there in operation continuous for 63 years. So as you see in front of you on the right-hand side here, this is one of our larger manipulator systems. It's mounted onto a gantry overhead and can be anywhere inside of a cell or large building, depending on where the gantries run. Those can also be pedestal or wall mounted and even deployed on a compact vehicle transport. So basically a lot of custom installations that we do with those. A lot of those go into black cells, or those are hot cells that do not have human entry after they're radioactively hot. So obviously hostile conditions there with harsh environment from radiation or similar environments. And some of the things that we can do with those, this gives you just a little bit of an idea. We have different grippers that can be installed on the end of the device on the actuator inside the hot cell. And there's one doing waste material handling. A couple other things here. One of the things I wanted to highlight, which we'll come back to here shortly, at our Shoreview, Minnesota plant, we have this large hole in the ground, as you see in front of you. It's actually a pit. We can flood that pit. And then as you see over here on the left-hand side of the pit, there's an additional 24 feet down diameter 10-foot diameter shaft. And what that acts like, for those of you that aren't familiar with commercial nuclear, is that is very similar to a core barrel with a refuel pond above it or a refuel pool, depending on what you're used to. So that gives us a lot of ability to test equipment and also do innovation for nuclear power plant refuel and decommissioning efforts. So pretty interesting piece that we have in one of our warehouses here for development. So our first project we're going to talk about was with Lawrence Livermore National Lab, and this is their National Ignition Facility and the boom lift. So summary of this project, as I said, this is with Lawrence Livermore National Lab. Originally, PAR in 1999 supplied the boom lift inside of the ignition facility, and that's to do all of their maintenance. So the scope of work for this is for PAR to do all the engineering, supply, integration of motors, sensors, software, wiring. This is a complete controls upgrade. We'll do inspection and evaluation of all the major components, and then anything that needs to be refurbed or brought up to current standards with current code compliance, we'll do that as well. And then we'll also do the factory acceptance testing. We'll deliver it back to site, help their folks install and test, as well as NERDL field inspections and then load certification. So all of that is currently happening, and NERDL is nationally recognized testing lab. So that's the outside of the National Ignition Facility at Lawrence Livermore. This is the inside of the target chamber. So this is inside the building. And then if you look down here where all this red piping and this is what that's showing you. This is that target sphere. So that's the inside of the target chamber in the facility. And then this is the actual target chamber inside. Uh, you'll notice this is the lift. There's two personnel on there, and they're actually going around to do maintenance on there. So this is the lift. So inside this target chamber at the National Ignition Facility, there's 192 laser beams. Back in December 5th of 2022, they delivered 2 million joules of ultraviolet energy to the fuel pellet to create fusion ignition. As you might remember from the news, this was the first controlled fusion experiment in history to reach the scientific energy break-even, meaning they produced more energy from fusion than the laser energy they needed to drive the experiment. So that was a pretty big next step towards realizing nuclear fusion power. So here's another picture, points out where our lift a little bit better in there. So as you can imagine, those 192 lasers and the associated mirrors and lenses require a lot of work, alignment, adjustment, and maintenance to complete this work. So currently that equipment, so this basket and then the boom and the lift itself are all currently at our facility, and we just began the process of inspection and evaluation for this pretty unique upgrade project. Okay, so and then the next thing I wanted to talk about, this is kind of more on our manipulator side. I wanted to talk a little bit about our nuclear waste management, decontamination, and decommissioning. So two of the big examples you see there are Fukushima and then Chernobyl decommissioning as well. So PAR designed and built systems for nuclear waste handling involving remediation and safe management of radioactive materials to mitigate their impact on the environment and human health. Currently, we're working on this on 3 different continents. So we'll talk a little bit more about how this work's accomplished. So on the left-hand side there is an overview cutaway of a boiling water reactor, a Mark 1 containment with a BWR 2 or 3, so very similar to what Fukushima has, and there's quite a few of those around the US as well and other places in operation. On the top left in orange, that's our gantry supplied, and then those wires going down to what we call a tensile truss. That's this work platform here, and then there's robotic arms off of that work platform. So that's a robotically deployed water jet that's on there, capable of cutting 500 millimeter thick steel. And then what that would be doing is a top-down removal of reactor internals and then segmenting portions of the reactor internals to bring those out, one piece at a time. So this is attached to what we designed for Fukushima. On the left-hand side is our concept for where we got through planning and design. In the middle there, you see the build where it was rebuilt. After factory acceptance testing, we then mock up. This was all taken back to Japan, or taken to Japan, mocked up there so it could be installed as easily as possible into the Fukushima units. So if you remember back to the pit that I talked about, that we have in the core barrel at our facility, we actually brought the crews over from Japan. They practiced and they qualified on our equipment in our pit prior to ever going over there and being in a radiation environment or having to deal with any of the other controls around contamination at Fukushima. So that was really helpful to our partners there doing the decommissioning work. So in the middle there, that's at the Yokohama facility. And then prior to deployment, as you see in the right-hand side picture there, that was deployed into Unit 3 at Fukushima to remove and transfer the fuel assemblies, as well as debris removal and inspections inside the core. So as I mentioned briefly earlier, there's really 3 main parts here on the gantry system. There's an auxiliary hoist, which is right there in the middle. There's a spent fuel handling mast, which is pretty similar to what you would see on a commercial light water reactor in normal operation, that they would be able to move fuel, whether it's spent or new. And then on the left-hand side is our tensile truss. And underneath, those are commercial off-the-shelf robotic arms that were able to be used on our equipment to do the removal and the disassembly inside the core. So this gives you a little bit of an up-close view of the tensile truss platform on the right-hand side and the robotic arms that went down into the reactor there for the disassembly. And then on the left-hand side, it's showing you basically what the underside of that gantry needs to be to support the tensile truss. So with that close-up view, you get kind of the underbridge and the robotic arm tool platform overview. So currently this machine is sitting, has completed its work, but they're looking into currently using this to continue the decommissioning work at the other units at Fukushima. So there may need to be some upgrade and some changes to it, but this, has the life to still has enough life left in it in a rad environment to move to another unit and continue the work that they need to have done. So one of the interesting things about the tensile truss is that it's actually an inverted Stewart platform. So it has the ability to do quite a bit of side load and offset load that you wouldn't necessarily think for a platform that's suspended from wire rope. Also has quite a bit of hardening already against earthquake and excessive accidental collision, redundant failsafe for drops, and you have quite a bit of depth, 100 meters or more as possible, very lightweight. And then the structural limits, if you look to the right, that's a normal telescoping mast. As soon as you get down, several meters, you're not going to be able to get much side load out of that or much ability to push against so that the equipment can do the job necessary to take apart reactor internals inside the vessel. So we actually developed this tensile truss for Chernobyl decommissioning. So those are the two bridges that were built to go inside the safe containment structure for Chernobyl, safe confinement structure, I'm sorry. So that was designed to prevent the release of contaminated material from the present shelter or the sarcophagus and protect from external impacts such as extreme weather. So that was built and then rolled into place with our equipment inside of it. So to give you an idea of the scope on that with the two 96-meter bridges, that right there is a human being standing next to it. So quite a large installation there. And then there's the quarter scale proof of concept model on the right-hand side that shows you the wire ropes coming down and holding the work platform. So we at PAR designed and manufactured the overhead bridge, gantry, and then the single failure-proof cranes required for the tensile truss, and then the manipulator system that was mounted on the bottom, which was used to move, drill, and then deconstruct inside of the safe confinement. Last December, there's been quite a bit of holdup with this work, obviously with the ongoing hostilities in Ukraine and the war there. So the European Bank for Reconstruction and Development in Ukraine is looking to get this work restarted as soon as they can, since it's been put off, and all of the equipment that's in there has been in a radiation field for almost 9 years. So likely there's going to need to be at the very least inspections and recertification on that equipment prior to continuing the work to dismantle and to decommission Chernobyl. So that's everything I had for today. As Adam said, we'll have questions at the end. I wanted to put my contact information here so that was available. Thank you.
Thank you, Judd. That was very interesting. There was a couple questions that popped up that kind of came along the same vein. What special measures does PAR take in order to protect your electronic components from the radiation fields that you're experiencing?
So one of the biggest things there is obviously is going to be shielding. Most of our equipment, unless if it's built radiation hardened, is 10 to the 8 rads that we go to protect against. So if you notice, we go back here a couple. These aren't electrical cables; those are wire ropes coming down. But then on our manipulator, a second, I thought it was closer than it was. I should have restarted. There's no all of the wire and all the electronics are run inside of the housing, which is going to provide shielding there as well. Another thing is also where the equipment is stored in the cell. If it's not in operation, it would be retracted and moved over, and some of it can be self-shielded if it turns on itself and is away from a point or a line source. That helps as well.
All right. One other question, I guess, that came up frequently was, is there an estimate of how long something like that would live inside of Fukushima?
What was the last word, Adam? I'm sorry, it cut out.
How long would a manipulator like that survive within Fukushima and within that reactor area? Would it survive for the whole decommissioning, or would you have to refurbish components?
I think that's the piece that we're going to need to look at. I know that we didn't have any radiation related issues with the Unit 3 decommissioning work that we did. And looking at it and how well it was operating, that's part of the reason that the operators and the Japanese conglomerate there is interested in moving it, is how well that system held up. Since it's in water, and water is a really good shield for gammas, and slows down neutrons well, it didn't really see that high of radiation doses. But I would have to talk to some of our technical folks and see there. But there is a maintenance kind of a pull it back, go through a refurbishment, look at it, see what needs to be replaced or what we would recommend to them replacing, because then the customer also has the option, they can run it to failure, and then we can, would have spare parts. There's different ways to, kind of skin that cat.
Great. Well, it was a very interesting presentation and looks like pretty cool, exciting work. All right, thanks, Judd. I'll now turn this on over to Christian for his presentation.
Thank you, Adam. Good morning, good afternoon, everyone. Hopefully you can see my screen now. So today what I've planned to share.
We certainly see you. I don't see the presentation.
Okay, just one more click here. There you go, that should be on. Okay, so this is what I've planned for today. So I'll start with a quick introduction on AtkinsRéalis, what we do in the nuclear sector. I'll briefly talk about our robotics capability, and then I'll cover two case studies that are ongoing projects. So, and I've picked these two because they're closely linked. They're both about a Glovebox decommissioning. So the first one is around remotely performing decommissioning tasks inside Gloveboxes. And the second one is about size reducing these Gloveboxes once they are empty. So I will cover those, and then of course we'll have a few minutes for questions at the end. So if you've not heard of AtkinsRéalis, we're a global engineering organization. We have close to 40,000 people across the globe now. And then in the nuclear sector, we have over 4,000 employees spread mostly around 3 regions. In the US, we do a lot of cleanup work for the DOE and also support new reactor technologies. Last year, we opened the AtkinsRéalis Technology Center that's in Richland, Washington, so close to Hanford. And that's a test bed facility with a high bay area that we're using for robotics and other technology development. In Canada, we have the Can-Do Energy business. That team has done a lot of work with robotics and automation, specifically around maintenance and refurbishment of Can-Do reactors. And then in the Europe and Middle East area, we cover the full life cycle from new build to decommissioning and waste management. And this is where the two case studies that I will present today have been developed. Then when it comes to robotics, of course, that's the focus today. And for us, it's about tackling the dirty, dull, and dangerous tasks on nuclear sites. So I'm sure a lot of you will have heard of these, the 3Ds of robotics. And that means we get to work with a wide range of technologies, from industrial automation technologies to automate repetitive tasks, to remote handling for remote work that cannot be automated, and also remote inspection for when we use mobile robotics to survey hazardous environments. And then across these technologies, typically our approach is to work with commercially available technologies whenever possible. And then we do the integration work around these technologies. So that being said, let's look at the first case study, which is the AtkinsRéalis Remote Glovebox Operation System, or ARGO. And that one started around 2019 after there was a serious safety incident at Sellafield in the UK. And at that point, a Glovebox operator got their hand punctured by a corroded probe. So the person received a dose of plutonium, and this kicked off a no hands and Glovebox initiative by Sellafield. And so what I'm going to present now is the solution that our team came up with. So from early on, our concept was based around this robot, the Kinova Gen 3 robot, which is really interesting because it fits through a 6-inch diameter glove port, which is the most common port size in the UK. And then the robot has around 39-inch excuse me, reach, a payload of around 9 or 10 pounds, and it can be configured in a 6 or 7 degrees of freedom configuration. So that can be really useful when you need a bit of extra redundancy for to avoid obstacles and avoid interferences. So this seemed like a viable solution to perform manual tasks. And through early trials, we've been able to demonstrate that, although it's not a robot that was intended for industrial applications, it's a very capable robot, and it has been shown that it can go beyond some of the specifications in terms of payload. And with over 400 glove boxes at Sellafield that needs to be decommissioned, we wanted an approach that would not need us to modify the glove boxes to introduce robotics. And so inserting the robot through the glove ports seemed like the best approach. So then to deploy the robot through a glove port, we need a stable base. So the platform has been designed to allow the arm to be deployed through a range of glove port heights. It has also an onboard power supply, so it can be wirelessly inserted through the glove ports without any trailing cables. And so it also fits through a standard doorway. So it's designed to be easily moved through existing facilities. Now, to maintain containment, we have a primary sleeve, which is equivalent to a glove. So same principle. You can see the installation procedure in this video here. And the sleeve attaches to the glove port on one end, and then to the robot wrist on the other end. So then the tools are outside of the sleeve and inside the glove box. Also, there's a secondary sleeve that is a redundancy measure in case the primary sleeve gets damaged by any sharp object. Now, once you have the robot deployed inside the glove box, you need different tools to perform specific tasks. We have a 2-finger gripper that we use for a lot of simple tasks, but we're also developing a toolkit for decommissioning, for size reduction, for different dismantling tasks. So you just saw a grinder. We've got this impact driver as well, and other cutting tools that we are developing for the glove box. So all these tools have a standard interface, and the tools are posted inside the glove box prior to operation. You can see the tool rack example on the left picture, and then the robot can automatically change tools using a off-the-shelf tool changer. So how do we control the robot? That's an interesting area because depending on the task, you can have a combination of teleoperation and automation. So if I play the first video on the left, that's demonstrating teleoperation using a device from a company called Haption. So that device controls the robot's position and provides force feedback to the operators. And in that case, the task is to apply the contamination gel with a brush and then to peel it off after it dries. So looking at the sequence, we can tell that it's something that can be done with teleoperation only, but there are a few repetitive steps in that process. So dipping the brush in the gel, for example. And so if we look at the second video, we can see that some of these operations can be automated. And we're not actually applying gel in this video just yet, but we can see that operations can be programmed offline in this simulator that you can see on the top right part of the screen. And then they can be executed live on the robot later on. So we're starting with the operation, but we will gradually build automation to reduce the work and the cognitive load for the operators as much as possible. One other element to mention there is that even when you're in teleoperation mode, it's possible to program bounding boxes, so virtual guides and walls to avoid any collision between the robot and the walls or windows of the glove boxes. Now, to add to the control system, we have this digital twin. So the purpose of the digital twin is, first of all, a training tool. So we can help operators train in a safe virtual environment. And I'll get back to this on the next slide. But also for investigation. So once you've got a 3D model of the environment, you can assess the situation, evaluate different methodologies. From there, established detailed procedures, including some pre-programmed routines. And then once you get to operation, you can use this digital twin as a tool to monitor the status and intervene as required. So we call this the supervised autonomy type of mode. Then one important module of the digital twin that is particularly important is this haptic training simulator. So this is an example that was developed by our partner Toya in the UK. And they've got this simulated Glovebox environment with virtual Kinova robots, and they program different scenarios. So right now the robot is picking up a block, and they have a few different blocks with different weights, so you can feel a difference with the haptics controller. You'll see this is now a assembly task that need a bit more dexterity. So with the latest developments in gaming and physics engine, we can really get immersive experience. And that's really important because we need a training system that will feel as closely as possible to reality, to operating the physical robot. And so that will allow operators to train in this virtual environment, in a safe environment, before going and using a physical system. And then, so in preparation for the deployment on site, we also organize a few operator engagement sessions. So you can see some of the highlights in this video. And it's a really important step to get feedback and see what works. How can we make the system as useful and as intuitive as possible? And also, what are the parameters that we need to adjust between operators, depending on their preferences? So for example, some operators will prefer a VR headset for visualization. Others will prefer just monitors with 2D camera images. When you look at this Haption controller, some operators will prefer different gains applied on the speed and force feedback parameters of the controller. So it's important to engage with operators and get that feedback considered in the design of our system. So in terms of where we are with this project, so it's been deployed for the first time in a contaminated glove box at the end of last year. So that was a duration of about 7 weeks. And that was a really important milestone for us. So we started simple with tasks like cleaning the contamination gel application, and gradually we'll increase complexity and deploy the system to other glove boxes. So we're still compiling data and results from this first deployment. So I can't really share too much details today, but we will be presenting at Waste Management next month. So if anybody listening plans on being there and wants to know more, that will be a good opportunity. I've got the session details on the screen, and I'll share my contact at the end if anybody has more questions. So that covers the first case study. I won't spend as much time on the second one, but I wanted to give you a flavor of what the next step is. You know, after a glove box has been prepared by the Argo system, the next step is likely to be size reduction, right? So this is what the Alpha glove box active demonstrator is about. It's about automating glove box size reduction to first of all optimize the packing. So in a drum in this case, but most importantly, to reduce risk to operators, because manually cutting these glove boxes involves a mix of conventional and also nuclear safety risks. And so it's exactly what we should be using robots for. So that's an overview of the system. We're using laser cutting. So we have a passive laser safety enclosure. The glove boxes are brought in the system from a door here on the right side of this picture. And then the output, the cut pieces are going to this drum at the exit on this side. And then outside the enclosure, we have air extraction unit here. And then outside the enclosure, we also have the various control panels for the control system, the robot, and the laser source and chiller. Then inside the enclosure, we've got a 6-axis FANUC robot with a positioning table that has another 3 axes, so 9 total. And then these are programmable vices. This is where we secure the glove boxes. And as you'll see in the video on the next slide, the cut pieces fall onto this vibratory conveyor. They travel towards this lift table, and then the pieces will fall into this the drum outside. So again, there's a sequence. The glove box is mounted on the positioning table. The robot has a laser cutting tool mounted on, and the glove box is positioned in such a way that makes the pieces fall onto the vibrating conveyor. And we're going really step by step in this video. We wait for the piece to be posted out before continuing. In terms of programming, one of the challenges here is that every glove box is unique. So the robot paths and the path planning has to be developed specifically for each glove box. And so we need to 3D scan the glove box. When it's outside of the cell, we start by 3D scanning it, creating a model, importing this into a robot offline programming software, and then we execute these paths that have been pre-programmed on live on the system. So right now the system is cutting a dummy glove box, a test glove box in active ways. And then once it's done doing the current one, we're planning to go into active commissioning in the next couple of months. So that's it for me. We should have a few minutes for questions, but again, my contact is here on the screen, and feel free to reach out if you would like any more information. Thank you.
Thank you very much, Christian. That's pretty interesting stuff as well. I got a couple questions. I tried to summarize them all up. How long does the for your portable glove box robot arm, how long does the battery tend to last?
Well, so the idea of the battery is not to have it powering the system during full operation. It's to give you the chance to insert the robot. Okay. To deploy it, then you connect it for power, and then you can use it for as long as you need. And so I'm not sure exactly how long it lasts, but so it's not a limiting factor for the operation. It's really just so you don't have to deal with cables during the insertion and removal steps.
All right. What kind of sensing capabilities or vision capabilities exist on the arm?
On the so assuming we're talking about the Kinova, yeah, the Glovebox remote operation. So so you can buy the Kinova robot with a built-in camera on the wrist of the robot. I think it's a 5-megapixel camera. In our case, we ordered the robot without the camera because it would be obstructed by the sleeve anyway. And so what we're using are cameras that are outside the glove box, and these are pretty standard CCTV type security camera. Just because we're not using the cameras for any automated hand-eye coordination, it's really purely for the operators to use when they control the robot. So nothing specific really.
For cutting up the glove boxes, about how long does it take to cut up one glove box?
Yeah, so good.
Case by case dependent.
It's case by case. So right now, because we're doing so very much step by step It took, I believe, about a week to cut our first and second glove boxes. That's what we have. But it's really, I'm guessing, a shift per day for about a week to really go through the process step by step, waiting for each part to be, outputted before we cut the next part. So, from an automation perspective, we could do much quicker. And so we'll keep accelerating as we program more glove boxes. But yeah, it's a few days to a week is what it took for the first ones.
How do you manage dust or chips that are generated from the cutting process?
Yeah, so we have a air filtration and extraction unit. So it's a off-the-shelf system. It's a system manufactured by Kranz, a German company. So that's what we use for to maintain the pressurization and collect the dust. But we also do a cleaning cycle. So after each glove box is cut, there is a bit of intervention to go and collect the larger pieces and debris inside the cell.
Interesting. All right. I think that's probably all the time we have for questions for Christian. I greatly appreciate the presentation. It was quite fascinating. All right, let's move on over to Scott, where he's going to give our final presentation for the day.
Hi, thanks, Adam. Get my screen here. So I'm Scott Martin. I manage the robotics remote handling division of Veolia Nuclear Solutions North America here outside of Denver. Excited to have this opportunity. Thanks, Adam. Thanks, Dan and ANS for allowing us to present. Actually, the CTO of VNS for the UK, Simone de Laval, was supposed to give this presentation. This is his presentation and his R&D project. But unfortunately, for all of you listening, you'll get the objectively less intelligent version from myself. But nonetheless, appreciate the opportunity, and yeah, thanks for letting me present. So the system we'll go through a little bit in detail today is an R&D project for fully autonomous waste sorting and segregation. So the vision of this kind of R&D, the vision of this platform was to provide a scalable, autonomous, integrated system for safe waste handling, for efficient waste processing, of course, trying to minimize human exposure and also minimize mixed waste packaging, so we can separate specific items based on their disposal route. This was started originally as a project with Innovate UK, competition in 2022 from our UK group. And we teamed with a number of other important partners. So VNS provided the system integration, the software integration, as well as a rad-hardened telemanipulator system, the Dexter robot you see here in the middle. And then we had a number of important partners. Faculty provided some machine vision and AI. Createch provided radiation sensing consultancy, gamma simulation. So for this particular project, we didn't use radioactive items, but we did simulate, what if a certain item were radioactive, and how do we see that through the sensing, and what do we do about that particular item? And Createch helped us with that. And as well, the University of Lincoln helped with some of the automation design for the system. So the kind of innovations required, or the steps for this autonomous sort and segregation development, there were 6 main things. The waste mix in particular was quite challenging because it was quite varied. So we didn't know exactly in the end what waste the customer was going to show up with. And the data available just in general for nuclear waste like this, it was very limited. So a lot of this project was teaching the system the types of equipment, the types of things it might see, how it identifies those wastes in the waste pile, how it picks up each of those individual wastes, autonomously, how it's characterizing what it's picked up, deciding what type of waste it is, ILW, LLW, and then optimizing its packaging. And the number 6 item there is really kind of the neat bit, and actually Christian had a similar slide on this, for mixing in the human supervision and telemanipulation when required. So of course the goal for this system was to do 100% autonomous work, but the reality is the waste forms are so varied, the situations are so unknown, what waste is going to come into the system, that having an ability to put a human in the loop to handle those edge cases is a very good situation for keeping the uptime of the system and not slowing down the other parts of the waste segregation and sorting because of one particular edge case. And of course, all of this is in a radiation area, compliant with nuclear storage policies. So here's a general flow diagram, kind of high-level flow diagram of the overall concept. The red part is kind of the area of focus for the R&D. So if we walk through it quickly, we're scanning items, or scanning the tray for particular areas, or just to get a general idea of what's in the tray as it's delivered. High dose rate items are detected. If they are, we want to remove those first, because a lot of times, those high dose rate items from a radiation perspective will blind the rest of what's in that waste tray. So we want to remove those first. The system autonomously will determine a grab pose for that particular item, or identify if that item is tangled in other items. After the system grips that item and lifts it, it'll characterize the item and then sentence it and place the item into its waste package. And then from there, we restart that process. So in this initial case, we're kind of scanning each object every time. It's not maybe a continuously running process. And a lot of the optimization going forward is in the software, right? A large part of VNS's job in this was integrating a number of different softwares to speak to each other and kind of go step by step through this process. So here's a view of the R&D platform, proof of principle. You have the radiation hard telemanipulator, Dexter here in the back, 2 RGB scanners on either side. And then we have a number of different AI systems for identifying the waste, sentencing and packaging, as we've mentioned. So looking at identifying the waste, here's some images of kind of what we're looking at with the scans that come off of this system. So that the top pictures show kind of a color image, RGB image, and a depth image of that system, or what's in the tray, I should say. And then on the bottom side, we see a little more categorization, maybe the combined image on the left-hand side, and then categorization of what it thinks these items are. It's interesting because we see some cases here, you can see this kind of angle that's laying on the bottom of the tray here. Initially, the system thinks, because it's being overlapped by something else, that those are 2 separate items. So this is part of the training that goes on here to help the system understand what could be a single item or separate items as the AI is working through the scans. So in terms of the machine vision, we have some kind of decision points. As we just showed, we look at the tray topology, identify the objects presented in the sorting tray so that the system will make its best guess of what it is. Select that object, especially the high dose rate items, for picking, and then the system determines a general grab position for that particular object. And you can see those a little bit here. where that system's wanting to grab each of those items based on its geometry and its position. So the grasping piece of it, in terms of the geometry and the position of that item, the system picks up those particular pieces by their maybe geometry as well as their location. So if we get some pieces that are on top of others or next to others, the system will prioritize which needs to get picked up first. So this is some of the testing footage that you can see. Apologies, it's maybe a little choppy due to the bandwidth. But as each of those are picked up, we do another scan to identify that item. So the particular item is picked off the tray, picked up, and we do another scan to get additional detail, match that to a number of possible items that could be in that waste. So in this particular case, based on that second scan, you're seeing, the system has a high confidence that this is a safety hard hat. Could be potentially plastic scrap or maybe a plastic bag, but in this case, we're very confident, or the system's very confident that that's what it is. And the force feedback for the telerobotic system is used to measure the weight, which also inputs to this. And in some case, if the system doesn't see, isn't sure, it can alert the operator. And then again, you're in an edge case where the operator can come in and evaluate what that system is, or sorry, what the item is that you're picking up. From there, we know the item, and we've picked it off the tray, and then it's really to packing optimization. The team went through a few iterations of this type of how best to package the waste inside of the waste container. So the first bit was a Tetris style packing, and that is, we take the object, pick it up, and then we find in the tray the best place to put that particular item. And then the inverse case was also tested. So the puzzle case where we look at the waste container and identify in that waste container where we might have space to fit an item that's in the tray. So then that particular tray item can be picked and fit into that waste container. Again, trying to minimize those packing volumes in order to reduce the ultimate cost of disposal for that waste form. So this speed at this stage of R&D is about 1 item per minute. And that's, again, based on a lot of the software integration between the various systems that are being used in this R&D. So then, to the edge cases, this is a visualization of, the arm picking up a cable, right? And it has an issue because it ends up running the cable into the edge of the R&D platform. So in that case, the user or the operator can come through to handle that particular edge case. And in a lot of ways, the goal eventually is to make this a more maybe learning on both sides situation between the AI and the operator. So when the operator picks or has to jump in for an edge case, the AI system can learn what was done. And similarly, from the operator side, the operator can get input from the AI system about what it's seen and what it's picking in order to better fulfill the disposition of that item. So the goal is to kind of work in concert between the operator and the AI as needed. So the next steps to this active demo is the active demonstrator. So we're looking at deployment of this technology for sorting fuel element debris in the UK. The plan at this moment is that system would be, not utilize the Dexter system because the radiation levels are not as high as would be warranted for that. But instead we can scale the platform that we've developed and use a more industrial robot to do the same type of tasks, have the same type of capability, but just at a lower overall dose rate. And with that, thank you very much for the opportunity. Happy to answer any questions. I will say as well, I'll plug, like Christian did, I'll be at Waste Management, and Simone will as well. So all your technical questions that I won't be able to answer now, he can answer them there as well.
All right, thanks, Scott. That was an excellent presentation as well. One of the questions that came in is there a specific reason why you didn't use LiDAR for scanning?
Oh, yeah, I think I'll leave that one to Simone. I'm not sure the design reasons that were that chose those specific sensors. Yeah, if you shoot me an email or shoot Simone an email, we can certainly get you an answer on that one.
All right. One of the questions also was, how did you simulate the radiation?
Yeah, so that was largely our partner, Createch, is what I understand. So they basically, from a software side, were able to take I believe it was an Envisage software, and simulate basically just that the sensing of that gamma radiation was coming from specific items. So in the testing, it would randomly select an item that would be a high dose read item, and the software would then feed back that this is a high dose item, even though the actual physical item was not radioactive.
When it picks up an object and then it decides that it's going to place it inside of the final container in a Tetris or maximizing storage pattern, does it attempt to calculate out that it might fall and roll into a different position, or does it recalculate after?
Yeah, we've clearly hit the limit of my technical knowledge of the system. I don't know the answer to that. I think we have done some physics-based modeling in other areas. My understanding for this particular R&D was it was just looking at a 2D space to place those items in. I'm not sure how much it considered the physics of what would happen after delivering those items to the waste container.
All right, I think that addressed the bulk of the questions, and we're getting pretty close to 2 o'clock, so I think we can go ahead and start wrapping everything up. Again, my name is Adam Carroll. I'm the chair of the Remote Systems and Robotics Division of the American Nuclear Society. And this will be hopefully the first of a series of webinars that we'll be hosting. This webinar was obviously focused towards industry, but next webinar will probably be focused on universities, and then following that, national labs. And then lastly, we will do a special topic webinar. We'll try to do one of these about every 2 months or so, depending on the pacing of how popular it is and how many people wish to participate. So if there is someone who is interested in being a presenter in the future, please go ahead and reach out to me, and we can try to coordinate and find out where you could potentially fit. I would like to thank everyone for participating. I would like to especially thank Dan for help putting this all together. And again, thank you, Scott, Christian, and Judd for helping support this and showing us some pretty exciting stuff today. And with that, I will close out the meeting. Thank you, everyone.